Sure. All right, so welcome to today's class. So as we see in our syllabus, we're moving on to week 7. And today's more about how to evaluate a machine learning technique. What are the metrics that are involved, both in the regression and the classification settings. The regression is more easier. There's more finer details and important ways to understand about how to evaluate a classification method. So most of the focus of today's slides will be on the classification evaluation. All right, so let's keep going. Yes.
Quick question. Last class we completed until feed-forward neural networks. So that would be it for the neural networks, or is there any other plan?
So the idea with the feed-forward was, so we divided the neural networks into the basic and advanced course. Okay. The idea was the neural networks to just focus on the feed-forward. The rest of the architectures are more towards deep learning. Okay. We can always touch on them in our revision class, etc., or in our project and stuff. I can give you finer details if you all feel like doing that. But if you want a full-fledged version of deep learning, then it's in the advanced course for now. But I'm willing to work around it. We can discuss.
Okay, cool. Thank you.
Yeah. Okay, so let's see. The beginning part of the slides are more towards cross-validation, so I would be jumping on them quickly just so that you have a recap. But these are the topics, especially these three are the main topics that one needs to be aware of. When someone does classification modeling or training and deploying models in the industry or anywhere, they always talk about these concepts, the ROC curve. It comes in every day, almost every other day in my office discussion. Someone or the other talks about some ROC curve for some model that they're talking about. So this is very important from a practical perspective as well. Okay, so there's some more goals in specific. There are different kinds of error rates that can happen. There's not one kind of accuracy. There are different kinds of things that can go good or go bad that we need to evaluate on. So these are just names for now, but we will discuss these. So we're going to talk about precision and recall, and false positive rate, and precision recall curves, which is basically a curve of this versus this. But these are all just different fancy names for now. We'll have more meaning as we go forward. This is more like a quicker recap. So these are the slides. I'll move quickly. So this is the setting. We have a labeled data set and supervised, and we are using a training set, and we're putting a test set aside. You choose some learning method. You do all the parameter tuning, cross-validation, everything. You have a learned model. And this is what we're dealing now. We are zooming in this part in this lecture mostly. How do we estimate the different metrics to evaluate your model? Okay, so say we had a simpler question. How does the accuracy of your model, of your method, change as a function of the size of your training set, right? 100 rows of training versus 1,000,000 rows of training. So you can always do those experiments if you had that possibility, right? But this is not a very useful analysis, because in reality, you have some amount of training. You don't have a choice on more or less, unless you are in a very specific setting. So as you see, the accuracy seems to be increasing with respect to different techniques on some particular housing data, not the Boston, but the California housing data. They use data and logistic regression. So they have some behavior based on how big your sample size is. All right, so let's see. Now, the question is this estimate of the curve good enough, or is there some error bar, right? If you see at every point there is this interval that you're looking at, which is like some sort of error bar. So basically, this is saying at these levels of sample sizes, on this particular technique, which is, say, logistic regression, this particular data set, they're not very sure about what the exact value is, but they're very sure that it is somewhere between 0.79 and 0.83. They don't know if it is 0.8 or 0.83 or 0.79. It's a bigger error bar. Here's even bigger. Here's like a huge error bar. But here, they're more confident as your training size increases. This is usually a known behavior. More the sample size, lesser the uncertainty, obviously. if your sampling is done reasonably well in terms of what is the phenomena that is generating the data. So these are more simpler analysis. We're going to talk about something even more as we go ahead. So there's also in this learning process, you already studied this, you've been doing some project work, and also you did some assignments on this. The learning process where you're really learning the method, if you zoom further there, you're basically having some sort of a tuning procedure that you're applying. So you're trying different kinds of models based on different kinds of parameters, and then you choose one best parameter, which gives you one particular model. Then you have your learned model, basically. Okay, now there are questions of, in terms of sampling, is one train test partition good enough? It may not be, it actually is not good enough, but it may be good enough for practical settings given your situation. It sometimes may not. So in that case, you might have to resample, generate different train test sets, right? This is what's going on here. Then there is stratified sampling. It's another kind of sampling where, say you had an unbalanced data set. So fine. When randomly selected training or validation sets, we may want to ensure that the class proportions are maintained, which means if you have an unbalanced situation where, say, one class has 90% of the records and other class has very few records in your data set, then when you resample and generate your train test splits, since we are talking about resampling, which means you can sample with replacement, so maybe you can do something called stratified sampling, which what it is doing is it's trying to do some sampling where the minority data set gets resampled more times, so that in your training and test, so the minority is in here, but in your training and test, there'll be more equality of the two classes based on this more biased stratified sampling that you're doing. So that way your model will not automatically say the answer to be always the majority class just because your original data set. This is still okay. Sometimes you might have extreme. Maybe all these are pluses of class one particular class and this is just class another class. Then your model, it doesn't really learn anything. It will say, hey, why to learn anything? Let's just always predict as class plus. I'll be getting reasonable success, right? So that's what model will get biased towards, just not learning but just predicting the same thing always. So to prevent that, you want to do stratified sampling. There are other techniques as well, like SMOTE, which is available in R as well as in scikit-learn in Python. So there are different kinds of techniques to deal with unbalanced stuff. So we're talking about all these because all these are in some way related to your evaluation or the training and tuning in terms of the evaluation process of your model, like how to choose the best model. Then we also discussed about cross-validation, the K-fold cross-validation. So this part I'm jumping on. So this is all coming in this process, right, where you're tuning the model. If you zoom in, you're doing cross-validation, you're doing better samplings to deal with unbalanced data. Before this, maybe you can say here you can do some pre-processing if you're dealing with missing data, etc. So this is your pipeline, which you're aware of by now. You've seen it multiple times. So this is just he's expanding on what K-fold cross-validation is. If he gave an example of a technique which is simple. Instead of SVM, he's using a K-nearest neighbor technique, but there, what it does is for your test row, for any row, in order to make prediction or classification, it looks at similar rows, K-similar rows, K-nearest neighbors, and then it averages or votes whatever the majority class is in the similar rows, and it predicts that as the class for your test row as well. Or if it was a regression, it just averages the value and predicts the average value, or the median value is the predicted value for the regression. So he's talking, so say cross-validation, can be applied to different techniques, but the goal is to use it to be able to choose which parameter has the least cross-validation error. So in K-nearest neighbors, the parameter is K. In SVM, you have cost and gamma. In neural networks, you have how many layers and how many neurons per each layer. In random forests, you have how many trees to grow, etc., how much to subsample. You're moving finally in this slide. Now you have some recap. I did this recap especially because we also had a break in the long weekend. I hope you all had a good long weekend. So now looking at the more of the content of the topic of the class, we want to evaluate a classification model much better and understand all the intricacies involved. So there is one concept of confusion matrix. So this basically looks like this. Say you had an example. You can build this for any classification model and any data set that you're using the model to make predictions on. So this is the actual class. This is the truth. This is what was predicted. This is what was predicted by a given model, for example. So basically, what is the context, just to have some story here? This is a model that looks at video. and then it tries to figure out what activity the person in the video is doing. Is the person bending, jacking, jumping, etc., waving, walking, skipping, side, run, different kinds of human activities, right? So basically, what the confusion matrix does is very simple. It basically counts the hit rate or the accuracy that was correctly done on a per class basis. Instead of overall accuracy, you might have overall accuracy something 95%, 99. It's a bad model, 5%, whatever it is. But this breaks down the accuracy on a per class basis. So if you had a 2-class problem, this is going to be a 2x2 matrix. So class 1, class 2, actual class, class 1, class 2, predicted class would be the labels. You won't have all these classes. In email, it's again 2 class, right? Spam, no spam, spam, no. Now it just counts how many of the true classes that are as bend have been predicted as bend. So 100% accuracy. How many true jacks were predicted jack? How many jumps is jumps? So here something going wrong, right? Actual class, only 89% of the actual jumps were predicted as jump by the model. So it made 11 mistakes. Now it also gives other information, right? It's a very simple representation. It's just some sort of a counting representation, right? So it tells us were all 11 mistakes that were made, because it's not 100% here, made by predicting a jump as different kinds of other activities, or were all jumps predicted as one particular activity? Here there's a pattern. All jumps were predicted as a skip that were made wrong. So all the mistakes in predicting jump ended up being predicted as skips. So if you think about it, jump and skip, skipping or hopping and jumping is kind of a similar behavior in terms of jump versus run or jump versus walk. So, I mean, I can understand there's some intuition here. We're not talking about math anymore. There's some intuition to reality. So the model got confused with respect to 11 activities, whether it was a skip or jump, and predicted a skip. 89% otherwise were correct. So and so. So what are we seeing here? There's a pattern developing. So let's see one more something here. Wave 1, 67% were predicted fine. 33% was predicted as wave 2s. So maybe there are 2 kinds of waving a hand or something, so it got confused there. But then there's a lot that had 100%. Now there's a pattern developing. If you have a good model, and if this was on your test or your cross-validation data set, what you would see is more and more bigger numbers in the diagonal and smaller numbers in the off-diagonal, right? The closer you're to 0, the better. And then you also have a more finer resolution of what kinds of errors and misclassifications happen. So this is very useful. Confusion matrix, it's provided very often. It's used very often in the industry or generally, whatever setting where you do classification modeling. All right, so if you had a 2-class problem, what are we looking at? I said our confusion matrix would be just 2 class, and there's 2 by 2, right? Because here you have a, 3, 6, 10 class problems. So you have a 10 by 10 confusion matrix, but in a 2-class problem like spam, no spam, you have 2 by 2 confusion matrix, positive class, negative class, or whatever. You can name it as whatever you want, class 1, class 2, or spam, no spam. But this here he wrote the other way, so he put in say, these are the actual classes, these are the predicted classes. It's the same thing. So what you care about is the diagonal elements. So you want the actual class positive, as many positives in the predicted class as well. So if the actual class is a negative, you want as many predicted classes as negative. So basically your diagonal number should be as high as possible. So this is a true prediction. This is a very common and standard notation. True positives, false negatives, true negatives. Very, very common. So true positive is a good thing. True negative is a good thing, which means how many of positives were predicted as positive, how many negative. Bigger the diagonal, the better. Off diagonal, there are 2 kinds of errors you can make in a 2-class problem. One is a positive can be falsely predicted. A negative, which something that is actually negative can be falsely predicted as positive. So this is false positive. So this is terminology that is used in clinical medical tests as well, right? If someone does not have tuberculosis, and if the test in the lab says falsely that you have a tuberculosis, that's a false positive decision. The person is not a patient. But if you test tuberculosis and you do the test on different 100 patients, and more the times you predict tuberculosis as tuberculosis, then it's a true positive. It's a better test. Otherwise, your test or your model is not good enough. So it's a very common notation. Some people also call false positives as false alarm, which also makes sense. Say you're doing fraud detection. If you falsely think a bank customer for some popular bank is fraudulent, then it's a false alarm. It's not true. You're thinking the model saying it's fraudulent, he's not. But if he's really fraudulent, we caught him as fraudulent, then more the catch, the better in here. So these are the different, very popular common notations. False negative, same thing, right? You can guess now. So anything that is truly positive but ended up being predicted as negative is a false negative. So if someone does have tuberculosis and the test is saying he does not, then that's a bad thing as well. There's a false negative. And if they, so this is true negative. If someone does not have tuberculosis, you don't want to predict him as tuberculosis. You do want to predict him as no tuberculosis. So this is the true negative. So what do you see? How do you come? So this is class-wise performance, like I mentioned in the confusion matrix in the previous in this slide. But if you want to know the overall accuracy, what you do, you add up true positive plus true negative by total. The total, if you add up this plus this plus this plus this, you would get the size of your entire data set. So that's a total. So this is the overall accuracy. But then if your overall accuracy is 90%, does it mean you're predicting 90% good on both classes? No, not necessarily. That's only one specific situation that could happen is 90%. Maybe this is 95%, maybe this is 85%, you know, individual. So on average, you have 90%, that kind of thing. Right? Is accuracy an adequate measure of predictive performance? No, because we clearly see from here, we care about not just overall accuracy, we see individual class performances and etc. as well. Okay. Also, if you have an imbalanced situation, so there's a large class Q, which means there's high imbalance. So maybe one class is very majorly occurring in your data set, then just by chance, if I blindly predict the major class as being my prediction always, I always make the same prediction, always say no spam, for example, because my data set was imbalanced. Then just by chance, I would have a very high accuracy, but that is not good enough. What you would have really bad is the other situation where whatever spam I'm predicting correctly spam, but when there is no spam, then if I look at my accuracy, I'll be horrible because that I'm not able to detect. Or the other way around, right? There is differential misclassification costs. So now, in a situation, so depending on the real life situation, this is more realistic, like more like consulting or real life situation, practical situations. The cost of a misclassification of one class may be very different from the misclassification of another class. So if you had a class 1 versus class 2, say a very common example, for example, is say if you were, this is used in the courts all over the world, right? You are innocent until proven guilty, right? So why do we do that? Because in that particular situation, the misclassification cost as perceived by the society of saying someone who is innocent, saying that someone is always guilty until you prove he's innocent, the cost you pay is very high because there may be a lot of innocent people who are treated as guilty and they might be getting a punishment or a death sentence. You know, a lot of wrong things could happen from a societal perspective that society does not like. So there, your cost is very different. Versus the other way around, where you are only considering the person to be innocent until anyone provides proof that he's guilty. Until then, he's treated as reasonably innocent. So same thing in medical domain, right? False positive versus false negative. Someone has cancer or tuberculosis and is falsely predicted. He's not predicted as being having cancer or tuberculosis. That's very dangerous. So that's a false negative cost. The cost to that is very dangerous because he's not receiving treatment at the right time. You're telling him he's perfectly fine, right? But if this false negative rate was low, then you're catching people very, very well. Other way around as well. Here, you're causing a lot of trauma to an innocent, to a patient, to a person who is no longer a patient. The person may be perfectly healthy, but you're saying, hey, you get this dangerous disease that might be, reducing your quality of life or whatever it is. Then you're just causing a lot of panic. So there is a different kind of cost associated to that. So ideally, you obviously want to reduce your false positives and false negatives, your off diagonals, right? But the truth is your model may not be doing good in all aspects every time. It may be doing good in some aspects and doing bad in some other aspects, or it may be doing bad in all aspects or doing good in all aspects. So you want to understand this very well. So this is very common terminology, and this is the situation when you're looking at a classification problem. For regression, it's very easy. You're predicting a real value. All you need is the mean square error, right? How away are you from the cross-validated mean square error? How away are you from the predicted value? There's no this class kind of a situation there going on at the highest level. Okay. So the true positive rate, so now we have other concepts, the true positive rate, right? So instead of just the count, you want to look at the rate, some value, right? Because one data set may have 100 rows, tomorrow another data set has 1,000 rows. Just these numbers are just raw numbers. You don't know out of how many numbers, right? It's just like your exam or a GRE exam, right? Out of how much is what matters. So if you want to compute the rate, then the true positive rate is basically the true positives by true positives plus false negatives, because these are all the positive bucket. So some were correctly predicted as positives, some issues happen. So that rate is what the true positive rate is. Similarly, the false positive rate is how many false positives were committed as a total of false positives and true negatives. Out of total negatives, how many? Out of total negative predictions, basically. All right, now comes very important point, ROC curve. This is very, very popular. So see, just doing ROC in my search tab in my Mac gives me so many ROC related stuff, okay? So this is just a quick example that I'm showing that. ROC comes up in daily industrial discussions almost very, very regularly. So this is something you really want to understand. I have different kinds of ROCs, Excel files, this and that. Okay, so, all right, now let's understand what this curve is. ROC curve is basically, you have, this is a standard curve, but so the x-axis is the false positive rate, your y-axis is the true positive rate. But then you may ask, if I have one model, I only have one confusion matrix, I only have one value for the true positive rate, one value for the false positive rate, which means I have only some one point, either this point or this point. I have just one value here and here. How am I getting an entire curve? Why do I have so many confusion matrices? Why do I have so many false positive and true positive? That's a good point. Now, every model has some sort of a threshold that you need to choose, or some sort of a parameter that determines the threshold. So as you change, so what does this threshold mean? Let me be more clear. Say if you did logistic regression, it's a soft classification model. So let me draw here. Oops, not Twitter, Twitter. Right. Any questions at this point, by the way? Okay, so in logistic regression, your output in a two-class logistic, because logistic regression is two-class, not multinomial logistic. So your output is usually it's very close to 0 or very close to 1. That's how it's classifying. So which rows will get 0 class, which rows get 1 class, that kind of thing. So it's a soft probability. So what you're predicting may be some number, not exactly 0 or 1. You're predicting some number between 0 and 1, right? That's your prediction. So you might have 0.75, then you say, okay, it's more likely to be class 1. 0.25, 0.15, more likely to be class 0, something like that. So I'm in the middle a little confused which class to put it in. So your threshold of where to cut off. So if you in terms of greater than that, it's class 1 and less than equal to is class 0. So would it be 0.5? It could be a nice idea. Maybe 0.5 is a good idea. But for some models, you have different kinds of behavior of these curves, right? Maybe sometimes you want to have this thing, sometimes this thing. But then you also want to, from a cross-validation perspective, you want to do the cross-validation error. You want to figure out the optimal fitting. You don't want to underfit or overfit, right? So training error keeps reducing, but cross-validation error, if you did k-fold cross-validation, for some choice of parameter, it is optimal. The least cross-validation error is what you're using in SVM, logistic, whatever. So the threshold also might decide that, right? Are you overfitting or underfitting? If you're required to underfit, you will underfit. Fit lesser than you. So if you're fitting somewhere here, then even stronger. If you're fitting, because you're underfitting, your error is too little complexity, but more error. Here, you're overfitting, too much complexity of models and more error. So then you want to reduce your complexity of that thing. So based on that situation, you can choose different thresholds of which, when you use how you map this output of your logistic regression model into either a class 0 or a class 1, right? So how do you choose one out of these two? This mapping can be decided based on this threshold. And you would say, if the predicted value by the logistic regression is greater than some threshold, then it's 1. If less than threshold, 0. But what is that threshold? So for different kinds of thresholds, you can draw, for each choice of threshold, you have a false positive rate and the true positive rate. So if you plot these thresholds, then you get this ROC curve. Now, what does this tell us? This tells us the different things. So say if I was in a fraud detection space and my model is being used for fraud detection. So then you want to control your false positive. This will help you choose which threshold to choose for your model and what is its business implications. So in a fraud detection setup, say I do not want to say a good customer is fraudulent. I want to have very less rate of that false positives because that affects my customer experience. So I might say I don't want my false positive rate to be greater than this value. So then my only choice is to see what true positive rate do I get at that value. Then it tells me I get some amount, 60% accuracy or 50% accuracy. Then I also know the trade-offs. If I allow for false positive rate much higher, then I have a higher accuracy. I get the whole picture of what is going on with my business. In some other space, you may be able to operate at a different FPR, at a different TPR, and based on that, you do this. And sometimes in some business space, true TPR matters the most, and you're okay with false positives, then you say, hey, I want at least 60, 75% false, true positive rate, the true predictions, the correct predictions. And I'm okay if I make 30% mistakes once in a while, then that's okay. That kind of thing in terms of false positives. So this is the ROC curve. And you can draw an ROC curve using simple libraries. That'll be your assignment. You'll use it in the project at some point. When you get to the evaluation part of your project, if you're doing SVM, neural network, or random forest, or all three, you can basically compute an ROC using these simple functions in R based on your model by trying different things as well. Or in Python. So now you can draw ROCs for different techniques. So you can compare BaseNet, naive Bayes, C5. You can try it here. Your techniques could have been neural network, random forest, SVM as well. Then you know what is the give and take you're getting. Maybe one model is performing well at a different FPR. So at this particular FPR, if this is what your company needs, you cannot make more false positives than this. Then you know at that FPR, this model is performing the best, the dark line. But here, not bad, not good, et cetera, et cetera. Here it is a very clear distinction. If you see this technique, until this band is performing better than every other technique. And here, these two techniques are similar. Okay. And then, but this technique is kind of horrible until the very end. So here, it doesn't matter here. All techniques meet and become 100% because here you're saying every time you're predicting the same class kind of situation. So I will always say it is spam. So whenever it is spam, I'm catching 100%. But how many am I falsely predicting as spam? 100%, obviously, because everything that is not spam also I'm calling it spam. So this is not what we care about. We care about a good accuracy. It's a lower false positive rate is what we care about more. All right. Now, another thing you can keep in mind is Bayes network, for example, is a little harder to train and tune. Naive Bayes is very simple. It's a very naive technique. So then if you're able to operate at this FPR, then why use such a complicated Bayes network? It's giving the same result as a very simple technique, naive Bayes. But if you really want to maintain low FPR and high accuracy, then you need to choose BaseNet. You get all these kinds of trade-offs. Another thing, how can we quantify this curve into one single number? What we care about is area under the curve. Just like the integration. If you integrate the area this curve, what you get is you get the area under this curve, the shaded area. So now this curve has lower area, this has higher area, this has higher area. What you need is a curve that is as high to 100% as possible at a much lower FPR, which means very small mistakes, but very high accuracy. That's a good model, right? So how do you get that? What is the maximum area you could ever get? That would be just the area of this rectangle, because you get something like this, right? So basically at almost 0% FPR and always 100% accuracy, like that's like magical. You would never see that in practice. This is a super simple problem. So then what is the area under curve would be exactly the area under this rectangle, which is 1 basically. So basically, your area under the curve, the closer it is to 1 or the 100%, the better it is. So you can also, there's a term called area under the ROC curve. So if I just did area under, there you go, area under ROC curve. It's super popular, used always, area under an ROC curve. So that'll give you just one number. So that's another metric that is very popular along with the ROC curve. Okay. Here he's talking about the different, trade-offs you have versus in terms of false positives versus true positives, etc. Okay, this is the algorithm for creating ROC curve. It's not, well, we can call it an algorithm, but yeah, it's not that tough. So you basically look at a threshold, and for each threshold, you compute the TPR and FPR, and you plot it basically. Okay, so this is some more examples of plotting an ROC curve. There are packages that do it for you. Okay, So, well, this is not very important, but it's good to know. Sometimes if you have too few points that you're looking at, you can always interpolate, like kind of smooth this, because you don't know what's happening in the middle. So there are you can always, these things sometimes could be done on your ROC curve as well. Okay, this is a nice question. Does a low FPR indicate that most positive predictions are correct? So what does this mean? You have false positives means what? So something that is not positive has been made positive, has been predicted as positive. So you're making less of those false decisions. Does that mean most positive predictions are correct? Not necessarily, because you're making low FPR, but your TPR may not be low; it may be high, or maybe it may not be high, it may not be low as well. So that's what this is about. Other accuracy metrics. Okay, so there is a concept of precision recall, which is the other curve we can look at from this confusion matrix. So the diagonal values are the true positives and the true negatives, and the off diagonals are the false. You want these values to be low, the false positive, the false negative. So the recall rate is basically the true positive by true positive plus false negative. So this one. And then the precision is true positive by true positive plus false positive, this one. So both, there is a trade-off. You cannot improve on both, basically. So if you look at curves, people also draw the precision recall curves. So you know what is the trade-off, at what recall, what precision would you get for any chosen threshold, and so on and so forth. So based on your threshold, these precision recall trade-offs keep changing. This is another example of an ROC curve. We've studied this already. This is an example of precision recall curve. So now the question is, since we care about not just training ROC or test ROC, you always care about cross-validation, right? Like you've been doing in your assignments and previous lectures. So question is, how do you get ROC and or the precision recall curve, both of these, when we're doing cross-validation? So approach one, you make an assumption that confidence values are comparable across pool predictions from all test sets, plot the curve from the pool predictions. So basically, what's happening is this, in this case. If you remember what's going on in cross-validation for any given parameter choice, in k-fold cross-validation, you have some different amounts of folds. And every time you're dropping a fold, right? So first time you drop this fold, you use this to train your model, and then you make your prediction with your trained model on this fold, you get some error. Let's call it CV1. Now same thing, you get this time you drop this fold, you use this and this to train, and then you predict on this, you get CV2. So like that, each time you drop one fold, since you have k folds or 5 folds, you have 5 CV1s, or k CV1, CV2, so on till CVk. So when you get the CV1, you're also getting the predictions, right? Based on that, you're measuring the error here. So basically, you can look at these predictions set plus this prediction set. You can combine all the predictions through this process and then use that to generate the ROC curve. In terms of looking how many correct and wrong predictions, you can have the confusion matrix and everything then, which is what he said, pool predictions from all test sets, and plot the curve from the pool predictions. Another one, plot individual curves for all tests. Here, you get a separate curve now. What you do is, in this prediction, you just get a curve for this. You get one ROC here, you get one ROC for here, you get one ROC is another approach. And then plot the average curve. So you get 5 curves, you average the curve, then you get the ROC curve. That's another approach. All right. Same thing you can do for the PR curve as well, the prediction recall curve. Any questions? Okay, so going ahead. So this is some high-level overview, again, of the ROC and PR, like a recap. So you can always read through this. So see the ROC curve, say the ROC curve is insensitive to change in class distribution. So ROC curve does not change if the proportion of positive and negative instance in the test set are varied. So that's a good thing. imbalance is not really hurting it. It can identify optimal classification threshold. So obviously, for your given your misclassification costs, you have a different cost for a false positive versus a false negative. So this helps you compute that, make that decision. Precision recall curve, it shows the fraction of predictions that are false positive. Well suited for tasks with a lot of negative instances. So if you have a very imbalanced data set, so in this imbalanced situation, this is more valuable, the precision recall curve. Because it tells us, are you doing good just because of a matter of chance, because you have an imbalanced data set, or because your model is really doing good? So that's what the precision recall curve tells you. Okay. And now we're having a quick segue. If you see our syllabus, which is this, let it load. Okay. So we covered these concepts. Okay, let's cover the F measure as well. It's popular, but people don't really use it that much in my personal opinion, because it's basically some sort of an average of the precision and recall. So let me show you the F measure. And you can it's a weighted average basically. So it's also called F1 score. So it is this. So this is known as a harmonic mean. So normal mean is, if you had two values, it's x and y, you have x plus y by 2, right? Or if you have n values, x, sum of all the values by n. A harmonic mean is this. You basically do 1 by x plus 1 by y. So precision recall can be combined, because precision and recall is a trade-off. You see that curve, right? You saw that curve in the slide. So basically what F1 score does is tries to boil that entire curve into one number for the precision recall. For ROC, we were having a nice situation where we were using the area under the curve. Here what this is doing some sort of an average value of the precision recall trade-off. So different kinds of averages and weighted averages you can do. One average is of this kind. It's known as a harmonic mean. That boils down to become this value, precision. So you can compute this individually, precision recall, and then compute F1 score. But then people can also have some weighting. Instead of having 2 in here, you can have some sort of a weighting. For any choice of beta, you have a different kind of combination of precision recalls that you would get. So this is the F1 score. But then always the question is, how do we know the right weighting to use? What is the trade-off? So you can use this, but you can just also look at the curve and understand the trade-off yourself based on where you are in your business, right? You can see ROC curve similar to the precision recall curve. You literally know what's going on. So this is visually good enough, in my opinion, actually. But yeah, it's always good to have that F1 score as an additional supplementary number. Now, coming back to our syllabus, which is here, we covered these things: confusion matrices, ROC curves, precision and recall, F measure, obviously, but these are the main concepts. Now we have this revision set up here for the next week. We can choose something that you're more interested in learning more about, or we can do a revision of all this, and we can also spend time on your project results and where you are in your project, etc. And see if you're stuck somewhere, so and so, and see how good your progress has been. So the next topic is kind of a little different. It's coming from a statistical standpoint. This is not machine learning per se, but it's kind of good to know. People use it a lot as well in different settings. So there's concepts of hypothesis testing and confidence intervals. So if you see in these slides, we are moving towards that part of the topic. So what I would do is I would leave the rest of the time for discussion if you have, or you can close early. You have 5 minutes early. Because I would like to catch on this topic in a more, from fundamentals in a more rigorous way in next lecture, because we're moving to the next topic. So we covered what is required for this part of the lecture today. Any other questions, concerns, comments? Yes.
Regarding my syntax. So the project you want us to do with like all the models, and like we learned a lot of models. Like you want us to apply everything and then go forward from there.
Yes. So basically, the end-to-end pipeline, like you wrote here in your email today morning.
Yeah.
I'm sharing my screen. Yeah. So yeah. Basically, yeah, the project is end-to-end pipeline. Like in reality, when you're given a project of this kind, they give you the data, you need to clean it, you need to have some idea about what your data set is looking like, then then deal with specific situations in terms of class imbalance or missing values, deal with that as part of the cleaning and pre-processing, then do the subsetting, and then do the modeling, and then do the evaluation. So basically, what we learned in this syllabus, almost everything, right? But you won't have to apply every single technique. You would do this. You would choose one or more techniques in here. More techniques, the better, obviously. But you would also do model tuning, which is cross-validation. Choose the best parameter for whatever technique you did. And then what we learned today would also be a part of your project, right? Because you want to give the evaluation metrics, right? Metrics are very important, industry, academia, wherever. So you're going to get these ROC curves, confusion matrices, precision recalls, etc., and understand the trade-offs involved there. So this is where your project would complete. So you're doing cleaning and training ETL here. You're doing modeling in here. The last phase is evaluation of your model. That's where you complete your project, basically. It's like a pipeline on your data.
Yeah, coming to those plotting techniques, right? Like we have a lot of plots, like ggplot and simple plots in R that we have. So in industry, what they generally use, like when you guys deal with real data.
That's a good point. So there are two ways of looking at it in industry. One, if you're looking for like nice, fancy visualizations for some nice businessy slideshow or something, then you can choose something outside R or Python. You can use some D3JS or something like that. But what is happening more regularly in terms of time sharing, people don't ask for fancy stuff. They want to understand the results and see how well their model is doing. So they're just using ggplot or standard plots from R or similar stuff from Python is more than enough. No one would do that for ROC curves. You don't need super fancy visualizations. It's just always a bonus supplementary thing that you can have, but your work is not judged based on how fancy and nice the graphics are looking. In the end, it's just a ROC curve, right? It's just the trade-off between TPR and FPR. They just want to understand that behavior. That's what is impacting the business more than how beautiful that plot is looking. That's it. That's what happens in the ML side of things or the data science side of things. That said, there are specific teams that are there to improve UI, UX, dashboards, and coming up with fancy plots and nice slides and beautiful presentations. So that's a completely different area, right? So there's a lot of different tools in there as well. But I don't see a lot of, I almost see none of that being used in day-to-day data science work in the industry, though.
Okay.
Yeah, but you would use it in other parts of the company as required, not for data science though. Okay, cool. All right, any other questions?
Hey Praneeth, will we get any assignment on the neural networks or?
So I wanted you to focus on the project actually. So just email me your project updates on where you are and where you're heading towards. And tell me which technique you're choosing to apply. Once you apply some technique, be it SVM or random forest, at that point you can apply neural networks as well. Then we can get back to this. I think the focus should be on the project at this point. That give you a bigger payback on your resume.
Okay.
Cool. I have one more question.
Yeah.
Like I spoiled my data generally. Like I just spoiled my data. So what I did was like I introduced a couple of NAs. So I have a question, like when we are classifying something, at the end we classify it whether it's positive or like in my case it's 0 or 1. So I even introduced NAs in that place. Is that a good practice or?
No, not in the supervised learning setting. Because supervised learning, you can introduce NAs in your input data. You assume your labels are always available. That is the supervised learning paradigm. Like the setting you're working in supervised is you always have label data. That is a good practice if you're doing semi-supervised learning techniques, because there's a different paradigm of learning called semi-supervised where you have partially labeled. Some rows have labels, some rows do not. Or if you're doing active learning where you have a possibility where you can query somebody, but you pay him a cost and then he gives you the label. These different settings, then you can do this kind of a simulation, but you can always add NAs on the X's, not on the Y's, on the features, but not on the labels, if you're planning to do supervised learning.
Okay. Yeah, because when I did that and I did Kane and impute, it gave me different values. So yeah, that's what I did.
Sure, cool. Yep, cool. Sometimes you also have to be aware of the fact that the garbage in, garbage out phenomena happens very popularly, where something comes out of your technique, but maybe what is coming out is garbage because we're feeding in or using it in a garbage. So that kind of thing also happens sometimes. Yeah. Cool. Anything else you want to bring up? Anyone? Okay, great. So we hit our 12 o'clock mark. All right, let's keep going. But all of you keep putting your efforts into the project. We will like to have a nice discussion and sharing stuff and results on where you are in progress in our next revision class. Apart from me spending some time on teaching some newer things, I can take this opportunity to teach you smaller topics, some other things. All right, cool. Have a good one, everyone. Bye-bye.
Thank you. Thanks, Benny.
Yep, bye.